Industrial scaling of synthetic sapphire is governed by extreme thermodynamics. The Kyropoulos crystallization process requires melting high-purity alumina at temperatures exceeding 2050 degrees Celsius. Maintaining this thermal state requires weeks of uninterrupted electrical baseload. Any power fluctuation lasting only milliseconds causes thermal shock, instantly cracking the crystal. The data reveals a compounding penalty when scaling ingot mass. Increasing ingot size from 85 to 120 kilograms extends the growth cycle to 22 days. This longer run consumes nearly 42 megawatt-hours of electricity. It also accelerates the volatilization of the iridium crucible, driving wear costs up by 56%. This degradation compromises the economics of larger runs. As ingot mass increases, average yield rates drop from 65% to 55%. The risk of microcracking during the cooling phase rises with volume. Producers face a structural trade-off between throughput and catastrophic batch failure. The physical bottleneck in crystallization is compounded by an upstream raw material deficit. Synthetic sapphire manufacturing consumes over 65% of global 5N high-purity alumina. This ultra-pure input is highly concentrated in specialized refining facilities in Japan and China. The data shows demand outpaced supply starting in 2023, creating a structural deficit. This deficit is driving a rapid escalation in material costs. The price of 5N alumina is projected to rise by 116% between 2020 and 2026. Producers cannot substitute lower-grade alumina to mitigate costs. Impurities exceeding just 1 part per million cause optical absorption bands, ruining the crystal for high-power laser and semiconductor applications. This structural vulnerability mirrors the synthetic quartz crisis of World War II. In the early 1940s, the Allied war effort was bottlenecked by its reliance on natural quartz imported from Brazil. The threat of maritime blockades forced a crash program to develop synthetic hydrothermal quartz. Today, the semiconductor and optoelectronics industries face a similar structural constraint. The frontier of advanced optics remains tethered to a highly concentrated chemical refining bottleneck.